Imagine you're a researcher, perhaps testing a new teaching method. You apply this method to one group of students, while another group continues with the traditional approach. After a semester, you compare their average test scores. Let's say the new method group scores a bit higher. The question that immediately arises is this difference truly significant? Is our new method genuinely better, or could this just be random chance, a statistical fluke? This is the core dilemma at the heart of much of statistical inference, distinguishing real patterns from the noise of randomness. On screen, visualize two overlapping bell curves, representing the score distributions of our two student groups. Their centers are slightly offset, but the curves overlap considerably. If we simply look at the mean of the new method group, which is a bit higher, it doesn't tell us enough. The variability within each group, the spread of scores around their respective averages, is equally important. If the distributions are very wide and overlap significantly, that small difference in means might not be convincing. But if the distributions are tight and distinct, even a small difference in means feels much more substantial. This is where statistical tests come in, acting as a structured way to evaluate the evidence. They help us quantify the probability that an observed difference is due to chance, assuming there's no real effect. This is the idea of a null hypothesis, which in our example would be that there is no true difference between the two teaching methods. Our goal is to see if the data provides enough evidence to reject this null hypothesis. Let's start with perhaps the most fundamental tool for comparing two group means, the t-test. On screen, show the two bell curves again, perhaps with their means marked. The t-test fundamentally asks, how many standard errors apart are these two means? Think of the standard error of the mean as a measure of how much sample means are expected to vary from the true population mean due to random sampling. If our observed sample means are many standard errors apart, it becomes less likely that they came from populations with the same true mean. The t-statistic itself is a ratio. On screen, display the formula, t equals frac bar x1 minus bar x2 se. The numerator is simply the difference between the two sample means. The denominator, se, is the standard error of the difference between the means, which combines the variability within each group and their sample sizes. Notice how this structure intuitively makes sense. A larger difference in means in the numerator will lead to a larger t, suggesting a stronger effect. Conversely, larger variability in the denominator, meaning more noise or overlap, will lead to a smaller t, making it harder to claim a significant difference. So, when do we use a t-test? Primarily, when we want to compare the means of two groups. If these groups are independent, meaning the selection of individuals in one group doesn't affect the other, we use an independent samples t-test. For example, our two distinct groups of students. But what if the data is paired? Imagine giving the same students a pre-test and a post-test. Here, each student serves as their own control. We'd then look at the differences in scores for and perform a paired samples t-test on these differences. The key assumption for the t-test is that the data within each group is approximately normally distributed, or that our sample sizes are large enough for the central limit theorem to apply, making the sampling distribution of the mean approximately normal. We also assume equal variances between groups for the most common form of the independent t-test, though there are adjustments if this assumption doesn't hold. Now, what if we have more than two groups? Let's say we're comparing 3 different teaching methods, or perhaps 4 different drug dosages. Could we just run multiple t-tests? For instance, comparing method A to B, then A to C, and then B to C? On screen, illustrate this with 3 overlapping bell curves, and lines connecting pairs for t-tests. The problem here is that with each test we run, there's a chance of making a type 1 error, falsely concluding there's a difference when there isn't one. If we conduct many tests, this chance accumulates, rapidly increasing our overall error rate. This is where ANOVA, or Analysis of Variance, comes in. On screen, show the 3 bell curves again. Instead of comparing pairs, ANOVA looks at the total variation in the data and partitions it into different sources. It asks, how much of the variation in student scores can be explained by the different teaching methods, the between-group variance, versus how much is just random individual differences within each method group, the within-group variance? The core of ANOVA is the F-statistic. On screen, display the F-statistic as a ratio. F equals variance between groups over variance within groups. Visualize the variance between groups as the spread of the group means themselves. If these means are far apart, this variance will be large. Now, visualize the variance within groups as the average spread of data points around their own group mean. If data points within each group are tightly clustered, this variance will be small. Think of it geometrically. If the centroids of our group distributions are spread far apart, and each distribution itself is quite narrow, then the F-statistic will be large. This suggests that the group membership, the teaching method, has a significant effect. If, however, the group centroids are close together, and the individual distributions are very wide and overlap considerably, the F-statistic will be small. This means the differences between groups are no more than what you'd expect from random variation within the groups. A large F value, then, suggests that at least one group mean is significantly different from the others. ANOVA, like the t-test, typically assumes normally distributed data within each group and equal variances. But what if our data doesn't meet these assumptions? What if our data is not normally distributed, or perhaps it's ordinal, like survey responses on a Likert scale? Here, calculating a meaningful mean might be inappropriate. For such scenarios, we turn to non-parametric tests, which don't make assumptions about the underlying distribution of the data. One of the most common non-parametric alternatives to the independent samples t-test is the Mann-Whitney U test. On screen, show two distributions again, but this time they are clearly non-normal, perhaps skewed, or even representing ranks rather than raw scores. The Mann-Whitney U test doesn't compare means. Instead, it compares the ranks of observations from two independent groups. Imagine combining all the data from both groups and then ranking them from smallest to largest. If the two groups are truly from the same population, would expect their ranks to be fairly intermingled. If one group tends to have consistently higher ranks than the other, that suggests a real difference. The U-statistic itself counts, for every observation in one group, how many observations in the other group are smaller than it. On screen, visualize this by showing individual data points from two groups and drawing lines from points in Group 1 to all points in Group 2 that are smaller. A large U value suggests that values from one group tend to be larger than values from the other. This test effectively checks if one group's values tend to be stochastically larger than the others. It's a robust test, useful when your data is skewed, has outliers, or is naturally ordinal. So, we have the t-test and ANOVA for comparing means when our data broadly fits parametric assumptions, offering power and efficiency. When those assumptions are violated, or our data is ordinal, the Mann-Whitney U test provides a robust alternative by focusing on ranks. The choice isn't arbitrary, it's dictated by the nature of your data and the specific question you're asking. Each test offers a distinct lens through which to examine your data, allowing you to move beyond simple observation and rigorously quantify the evidence for or against your hypotheses, helping you decipher if that observed difference is truly a pattern, or just the beautiful chaos of chance.